is Darren Gates, and I'm going to be guiding you through this small presentation about RVSM, in particular relating to maintenance issues. So to give you a bit of background about RVSM, first of all, over the last several decades there's been an ever increasing amount of air traffic, and there was a requirement to increase the number of aircraft allowed in proximity to each other in order for us to maintain the traffic or keep up with the demand of the increase in traffic. The problem is, prior to the introduction of RVSM in 1997, aircraft were separated by 2,000 feet at flight levels above 290. And the reason they had this was that there was known inaccuracies of the instrumentation at higher altitudes with the technology at the time. It wasn't until the 1990s that air data computers and altimeters and autopilot systems became sufficiently accurate to safely reduce the vertical separation. And so from 1997 onwards, gradually in different airspaces around the world, RVSM has been rolled out, and it's for aircraft above flight level 290 and up to and including flight level 410. So RVSM decreased the separation from 2,000 feet to 1,000 feet at the flight levels between flight level 290 and flight level 410. Now, because of this reduced separation, it had to be ensured that the aircraft instruments were of sufficient accuracy to safely fly in these new flight levels. And moreover, the aircraft maintenance program also needed to reflect the need to ensure continued accuracy. And that's what we're going to be taking a look at in this presentation. So how did this whole process begin? Well, the first thing, it starts with the manufacturer. He has to assess whether that particular aircraft is capable of meeting the RVSM criteria. And if it does, he will certify it as such. What he also had to do was produce a list of RVSM critical components that is required to fly in RVSM airspace. The maintenance program also had to reflect the need to ensure RVSM capability is maintained, and that includes developing procedures to ensure RVSM is compliant as a result of any maintenance action that's carried out on any defective components, and the flexibility to dispatch aircraft under MEL in the event of defective components, but still ensure that it's correctly documented, and where it needs be, that everyone is aware that should a particular component be dispatched as under the MEL, then that aircraft is not allowed to fly into RVSM airspace until such time as it's been rectified. And then we have to have procedures to basically recertify the RVSM. So what basic equipment is needed? Now, this will vary from aircraft to aircraft, and you would need to check your specific aircraft, but generally as a rule, generically, you must have 2 independent altitude measuring systems, secondary surveillance radar, altitude reporting transponder, an altitude alerting system, an autopilot, and the flight crew have to be approved with a specific authorization and go through a training program in order to fly into RVSM airspace. So let's look at the maintenance issues specifically. Now, apart from all those critical components or minimum equipment that we saw on the previous slide, apart from those LIUs and specific LIUs that we need for it to be RVSM capable, Most manufacturers will also define an area of the skin surrounding the static ports that they will then define as RVSM critical area. And any damage in this area, no matter how small, has to be assessed and has to be proven that the damage is not affecting RVSM performance. And the normal way we do that is to do a skin waviness test or skin mapping. So let's take a look at the skin mapping process, or skin waviness test, sometimes it's called. So this involves the accurate mapping of the skin surrounding the static ports or within the skin within the boundary laid out by the manufacturer that's the critical area. It is carried out if any damage is found in the area to prove that the aircraft is still capable of RVSM flights. And it's also carried out as part of the RVSM continued airworthiness requirements. Typically, the inspection period is 24 months, normally aligned with one of the larger checks. But again, manufacturers vary, so you need to check. The usual method to map the skin is to use an accurate digital depth gauge and a special bar that slides along it, and you take measurements at specific points. When the completed data in the depth gauge is downloaded onto a PC, it is then sent away for analysis, or sometimes the OEM provides you with an Excel spreadsheet to download the information into. You will be measuring quite a number of points, probably in excess of 200 or 300. You'll be taking 200 or 300 measurements, possibly more. Every manufacturer will have a slightly different procedure, but generally the following method is kind of common. So the OEM will provide a special kit specific to that airframe to carry out the skin waviness test. This kit will include the measurement equipment as well as a template for marking the measurement points on the skin. So you place a template on the skin, taping it in position, making sure it's aligned with the reference points, and then using a dry white marker pen, mark the measurement points on the skin, and then remove the template. Then you have to set up the measuring equipment, and it's important that you set this up correctly from the outset, otherwise you'll run into problems. But basically what we have to do is, number one, make sure all the memory bins in the depth gauge are empty, and on the ones I've used before, you have to go through every individual memory bin and delete the contents to make sure it's all empty. The gauge is then zeroed by placing it on the bar and setting the zero datum. And you also have to make sure that the gauge reads in the correct sense, i.e. when it moves in, it records a positive number or possibly a negative number. The AMM procedure will tell you. And when it moves out, it stores either a positive or negative number. It depends what it says in the AMM procedure. Normally you'll need 3 people to do this task, 2 people to hold the bar and 1 person to take the measurements. You may get away with having 2 people, but you'll definitely need at least 2. 3 is ideal. First step, then place a bar on the skin, aligning it with the reference marks. Now it's really important that the bar is held in position and is not moved while you're taking the measurements. If you slip, then you really need to start that batch of measurements again. It is also important to make sure that the measurements are started from the correct starting point and are taken in the correct order. Otherwise, if you do it all higgledy-piggledy and don't start at the right place, when they produce a skin map, it'll be completely, it won't make any sense at all. So start in the right place and go and take the measurements in the right order. So you slide the depth gauge along the bar, taking the measurements at the specific points. Then you move the bar down to the next reference line and repeat the whole process until all the measurements are taken. Once all the measurements have been taken, the depth gauge now needs to be downloaded of all the data. Now from here the procedure will vary according to the manufacturer, but typically the data is downloaded into the OEM supplied Excel spreadsheet, and you'll find the data from the depth gauge automatically pre-populates the spreadsheet cells. Now it depends on the manufacturer, but the spreadsheet may give you a go, no-go status immediately, or the spreadsheet may need to be sent away to the manufacturer for analysis, and then they'll come back to you with the results. Okay, some other points to consider. Now, if a static port is replaced, you will need to do a flushness test on the static port after it's been fitted. Typically, the AMM procedure for replacing the static port will refer you to the full skin waviness test procedure. However, normally it will not require you to do the full skin test. Instead, it will refer you to specific paragraphs or pages to take specific measurements around the static port only. But again, every manufacturer will have a different take on this, so you'll need to check. Just to highlight, there are different methods of mapping the skin actually, including using a laser scanner type tool. I've never used one of these. I've always used that traditional depth gauge one, but there are other methods available. There are some verification or monitoring programs that you need to be aware of. Now, to be perfectly honest, I'm not sure if this is widely used anymore. Certainly when RVSM first was introduced, then it was. But I think the confidence in instruments now is such that this is kind of becoming obsolete. And as I said, in my experience for the last few years, I don't recall any of our aircraft actually performing this check. But initially, certainly in the beginning, there was a requirement for monitoring because of the need to keep the aircraft safe and have confidence in our instrumentation. So operators wishing to operate in RVSM airspace are required to participate in the RVSM height monitoring program. Height monitoring is achieved by overflying either a ground station, and there's several of them scattered around the world in certain locations, or by the onboard carriage of a GPS monitoring unit or a GMU. So the HMU is a passive ground-based system that measures aircraft height within its area of coverage. Each system consists of a set of ground stations arranged as a central site with 4 additional receivers arranged in a square. Each site receives the aircraft's secondary surveillance radar replies, so that's from the Mode A, C and S, from which the 3D position of the aircraft is derived. Using meteorological information and the Mode C or S height data, it is possible to calculate the altimetry system error. For a successful HMU measurement, the aircraft must remain in level flight for about 5 minutes between flight level 290 and flight level 410, i.e. within RVSM airspace, within the coverage of the HMU. The HMU in Europe are based in Austria, Nattenheim in Germany, and Geneva in Switzerland, and you can see the latitude, longitudes there. The other method is using a GPS monitoring unit. So this is portable, you carry it on board the aircraft. It's got 2 independent GPS receivers, 2 separate satellites, and a device for storing the data, the GPS 3-dimensional positioning data. So the GMU is positioned on the relevant aircraft and functions completely independently of aircraft systems. It's entirely standalone. Once a flight has been completed, the recorded data is then sent to a central site where, using differential post-processing, the aircraft altimetry system error is then determined. So to summarise then, in order to operate in RVSM airspace, the aircraft itself must be certified as RVSM capable. On older aircraft, a number of service bulletins may need to be accomplished in order to achieve this. The OEM will then provide you with a list of critical equipment to ensure continued compliance. So although some of this critical equipment can be MEL'd if it is US, the aircraft cannot be flown in RVSM airspace until it's fixed. Now that's fine, but bear in mind from an ops perspective, there will no doubt be a fuel penalty to pay because the aircraft have to fly at lower levels. Any damage, no matter how small, including paint flaking in the critical area, has to be assessed in accordance with the AMM. And company procedures may require maintenance people to be specifically trained in RVSM before they're allowed to work or certify on RVSM components. That's down to the organization's exposition and procedures. But every company will have a different way of doing things. So you just need to be aware of that. I believe also there is a requirement to do RVSM continuation training as well, but most companies will incorporate that into their normal continuation training.